heavy like meetups, but we don't have anything in the middle. This meetup tries to kind of bridge the two. So yeah, like I'm Arnie. I'm one of the many organizers, and if we're always looking for speakers, so if you would like to speak, or if you would like to talk about something, just reach out to one of us. And with that, also these are the companies that are hiring. Like, I guess first of all, so the way we do it is actually first we'll just go around the room and just introduce ourselves, and during the introduction, if you have any announcement, you can just announcement like, oh, if you're hiring or if you're looking for someone, just feel free to just shout it out. And yeah, I'll just start with that. Matt, do you want to first introduce yourself?
Hey, I'm Matt. I'm going to be doing this talk. I work for a company called Embellis. My CEO is right over there. Say hi, everyone. So I need to say that we are hiring. We're looking for an associate data scientist, front-end UX, UI kind of engineer person, full stack. Just come talk to me afterwards if you're interested in, Or talk to David. Actually, that's a much better idea. That's David over there. Sorry, everyone on the stream. But yeah, so our company, which Rebecca would be much better at explaining, essentially what we do is we take a game-like assessment and we try to predict just how far a job applicant would go based off of how well they do inside of this assessment. I build some of the models that predict just how well a job applicant would do based off of different kind of psychometric principles. Yeah, that's about it. I also do stuff like this at work. So if anyone's interested in that, yeah, come talk to me.
Cool. Right, so I'm Arnie. I'm one of the organizers, like I said. I work at a company called Flipboard. I'm a machine learning engineer there. And we are hiring, I'm not sure what role actually, but we are hiring one senior iOS developer, and we're always looking for machine learning people, so talk to me if you're interested. Just go ahead.
Sure. Yeah. Hi, I'm Osama. I work with Streamlabs. We are, if you've ever seen kids play games and make hundreds of thousands of dollars a month, they make that money through our platform, and they also use our software to stream out the video games to Twitch or YouTube. We do machine learning actually. We do very low level C++ based computer vision and GPU optimization based video encoding, which is based on machine learning. So we're looking for machine learning folks who are excited about C++ and GPUs, ideally. So yeah, come talk to me if you're. And I help organize this.
Hey everyone, my name is Anchan. There are beer reservations this evening, most importantly, at the local in Gastown. If you're heading down after that, you can walk together. I am a machine learning engineer with a background in speech processing. I'm doing interesting stuff in brain health at the moment.
Oh,
yeah.
Yes. Hi, I'm Kevin. I've come actually from New York to Vancouver, trying to look some things in machine learning and data science, and so I'm basically trying to make as many contacts and networking as possible in the topic.
Hi everyone, I'm Bart, software developer, moved here from Belgium. I'm currently working on an idea that would use machine learning as part of it, so I'm trying to find out as much as possible.
Hi, I'm Bill. I'm looking for clients with large industrial processes that need optimizing.
I'm Paul. I work at Central Credit Union as a product manager. We're focused on customer retention. We generally hire, there's always some kind of developer role open there. Come chat with me if you're interested.
Alexi, machine learning engineer, and come back on Thursday to see
Data science like
Paul and I talking about essentially what data science and machine learning for product managers.
Yes, and trying to connect the data science community with the product manager for the first time.
And by back, we mean like here.
Yeah, it is here, actually, right here. Yeah.
I'm Kelly, a freelance developer, mostly Python, but lately C and C++.
I'm Ian. I've been a long-time Python developer, also C++. Image processing is my specialty.
My name is Justin. I work at Best Buy as a business analyst doing process analysis.
Hi, I'm Steve. I do data science at Valpad. We're also hiring a bunch of engineers and a data analytics manager. So if you're interested, come see me.
Hi, I'm David. I'm a data scientist and I work with Matt at Bellis.
Oh, we were supposed to mention that we pay American.
Oh yeah, that's right.
Well, we pay American.
We do too.
Alex.
I am Jody. I'm working as a data scientist in Ritchie Brothers.
So I'm Ali. So I'm doing the same thing. And before Ritchie Brothers, I was working for them as a data scientist.
Hi, I'm Robin. I work for AgFunder, a VC in San Francisco focused on ag tech investing. I'm head of engineering there, which means data science is part of my job. These days on the side, I'm focused on deep reinforcement learning in Python.
My name is Morgan. I work at Hootsuite as a data analyst. I focus primarily on user behavior and product data, and we are actually hiring as well.
Yeah, sales only me, and it's my first engineering.
Thanks for the pizza already. That's good.
My name is Tony. I have a background in machine learning, and right now I'm working in quantitative trading. I partner with a New York hedge fund, and I'm writing my models and interested in speaking to people who are working that area or interested in that area.
Hi, my name is Vincent. I'm building out a VPN service, but I don't have enough resources to compete. So I'm probably going to be looking for work.
My name is Ray. I'm a student here at SFU. I'm doing my big data master's. I also did MBA back in States. I'll be graduating soon, so just here to learn pretty much.
I'm Davey Dooley, and I work out at Center for Disease Control near City Hall. And pathology. And we are interested in bringing ontology into the business of data analysis. And so we're looking to grant a bunch of money for oncologists. This small, and if you want to know what ontology is about, please come to talk to me. Basically, we're trying to normalize all the data that comes in according to internationally agreed upon standards for the measurables, the variables, the categories, the nominals, so that we can then let you guys go crazy with the data analysis analytics.
Hi, my name is Zoe. I just graduated from the Master of Data Science from UC. My interest is in natural language processing, and I have been working in some project in NLP, and I'm also interested in deep learning. I'm looking for jobs.
I'm Tyler. I'm also a recent graduate of the MBS program at UTC, and my background is in economics, finance, and in small trading sort of stuff.
I'm Sid. Like them, I'm a recent graduate of Master of Data Science from University of British Columbia. I have a background in software development, and I'm looking for jobs.
Hey everybody, my name is Dane. I'm a small business owner. I own a little restaurant in Chinatown. I'm also a crypto trader because we've been accepting crypto at the restaurant since 2013. It's also my birthday.
Happy birthday.
My name is Mara. I'm new to Canada. I'm a data analyst. I have some background studies in artificial intelligence, but it's on full time, and I'm trying to update my knowledge and learn data science.
Hi, I'm Jade. I'm a software developer, and I dabble occasionally in machine learning.
My name's Rob. I do data for a startup in Vancouver. Right now I'm building a recommendation system. If anyone has experience with that, just chat.
Hi everybody, my name is Boris. I'm one of the organizers of PyData as well. Actually, a side story. I've been traveling in Japan for a few months, so I haven't been organizing as much. But actually, when I was in Japan, I did a small talk for the Osaka Kobe Meetup group, which is almost a parallel sister organization of what we're doing here in Vancouver. And in fact, I talked about productionizing ML models, just by chance. So I'm really excited that we are actually merging the three groups together with like Rogue ML, Production ML, and Friday together. I'm sure we've got a lot of common interests and common ground between data science and data engineering. And if we're any friends that's like on the other side that might bring them together, please invite them to come along and join us. There is beer and pizza. Thanks, Anish, for that.
I'm Anish, the Director of Technology here at STAT. First of all, thank you all for showing up. Some people say that Real-Time is a bit further away or whatever, and you're organizing a meetup, you don't show up. So thank you all for showing up. It's really good. I'm really happy that we're doing these data meetups. We want to do a lot more of them. I believe in 2 days you're also doing a product-based data meetup. Yeah, that's pretty awesome. So here at STAT, what we do is we collect a lot of data from search engines. We collect a lot of data from Google and Bing primarily. Talking about like, we're searching about 10 billion keywords on Google and Bing every day, pretty terabytes of information. There's a few, we're hiring for quite a few different roles. A few data engineers, a few full stack developers, a team lead full stack. Data science perspective though, I'll talk a bit about why that's interesting. So Google kind of, there's a few things, right? It presents people information from a particular location, like they'll specialize in giving you results for gas stop. You search for gas stop. And so collecting data from Google at a very large scale is actually quite difficult. And so we do a bit of analysis right now in figuring out how to do that and how to measure that the quality of data we're collecting is good. But there's a lot more machine learning we can actually do. We've not actually gone to that level yet. We just do basically the analysis. So that's a very interesting challenge. Parsing all of our HTMLs that we collect and categorizing them is a very interesting challenge. And then what we want to build right now for our next year is topic modeling on all the keyword data that we collect. So we want to aggregate that up into lots of topics and then analyze all that data. So if you're interested in data science or any of these things I'm talking about, come talk to me. We have a few people in the back too, Owen, who's our SDM. And talk to them about this stuff too. We're really interested in growing out our data science team. We don't have any data scientists right now. I'm going to grow onto a team of at least 2 by the next year.
We have lots of positions that will be opening up shortly. You'll be showing on our website, but if you'd like to see here, see it. Come talk to us.
Hi, my name is Ahmed. I'm currently a third-year CS student at SMU, and I'm working as a co-op student in Environment Canada as a data scientist. I'm here to learn more about machine learning as well as artificial intelligence. I'm also here to look for a job next summer.
So I'm Steven, and I'm mostly here at network. I'm also interested in marketing analytics, which I'll get into in a bit. But anyway, so I recently graduated college, and so I've been looking to do more work, maybe get a full-time job. I have about 3 years of experience, part-time, with web development and SEO and stuff. And I'm thinking about learning about analytics. And also I have my cards here if anyone wants, so I kind of know how to
I'm Daniel. I'm more on the systems programming side. So as the saying goes, you guys design the plane to be visible on radar, and I'll teach that plane to fly. So whether it's the back end is Rust or Pythons or spacey people or whatever, so that's my side of the world. The startup in that probably isn't viable, so I'll probably be looking for a job really soon.
I am Mahmoud. I'm a software developer and more interested in data science.
Hi, I'm Aaron. I'm a mathematician. I do stuff that isn't really data science most of the time, but I dabble around with machine learning and data science.
My name is Dion, and I'm learning Python, so this seems like an interesting topic to start.
Hi, my name is Dylan. I'm a software engineer here at STAT.
good?
So, yeah, like actually, do you guys want to get intro or?
We're just trying to.
All right, cool. Then, all right. We also have a couple of announcements. The bathrooms are downstairs.
Just go down the stairs and along that wall, the rooms there, the bathrooms.
And we have, well, we probably missed a couple, or did we? We did.
I think we got everything.
Yeah.
All right, cool. If we like, so yeah, this is the hiring list. If you guys want to reach out to people, here's the. And also, we have a Slack channel. Like, if you would like to just stay in touch with us, like, you can find us on like vantech.herokuapp.com, and these are the 3 channels that are most relevant. RogueML discusses most like NLP based things. Then we have production ML and PyData. So these 3 are the channels of interest.
There's also information about this on the comment section of the Meetup page today.
All right. With that, let's let Matthew just start his talk.
Okay, I will. Yeah, so first of all, if anyone has any questions during the talk, just like go ahead and ask me, and then I'll try to remember to repeat it for the people streaming. I prefer to do it in a conversational style, so you're really not bothering me. Go ahead and I guess try to stump me, I guess. Don't be too mean, though. All right, so Hyperopt-Sklearn, really simple hyperparameter optimization. That's a lot of words, and right now we kind of only understand really in simple, and my goal is to kind of get all of it. So who am I? So I also got my master's degree from UBC. Oh, can I do this? But now can the webcam see me?
They're okay.
Hi. It's going like directly at me. Okay. As I said, I'm a data scientist at Embellis. Do you want to see if this is
It's okay. It's okay. You're good.
We build simulations to predict problem-solving abilities of job applicants. We are hiring and we pay American dollars. Again, my CEO demanded that I go say that. It's a great company to work at, by the way, so please come and give me your contact information. So the way that I formatted this talk was to try to answer a bunch of different questions. And you could kind of imagine this talk as being like, you know, pretty simple, just get everyone to the same level, show actually what we need to be doing, and that's the why should I care about this? I'm actually going to go right to what would normally be the conclusion of this talk, and then I'm going to spend a lot of time talking about math, and then hopefully you understanding where this math is going to actually like make you care about the math a little bit more. A few more questions, but again, that's about where we're trying to get to. So again, we're starting at the very beginning. We're talking about machine learning. So machine learning is about finding parameters for a model to minimize some loss function. And you can say this generally, this is supervised learning, by the way. So whether that's a linear regression or a random forest or a neural network, it's all based on the same idea. You get some amount of information from this loss function. You want to minimize that. The other important thing to remember is every algorithm comes with a different set of assumptions. So for a linear regression, obviously everything is going to be linear, which is a pretty crazy assumption to make, but it also just happens to work really, really well in a lot of different cases. And I would suggest that you always start with that. So now we know what a parameter is. It's like a coefficient or something like that. What is a hyperparameter? Well, any kind of assumption that you make about your model is going to be a hyperparameter. So the first assumption you might make if you're doing a linear regression might be your regularization strength, for example. But actually choosing a linear model itself is also a hyperparameter. And you can imagine that different hyperparameters are going to be conditional on each other. That's going to make this pretty difficult. All right. So right here we have a lasso regression, which is just a regularized regression. And we have a very small regularization strength. And then the same model, only with a stronger regularization strength. And then we're training on the synthetic data that I made. That's about, let's see, there are 10 features here, 5 of which are informative, right? And it turns out, if you look all the way down here, that lower is better. That this low alpha hyperparameter actually does better than having something that's highly regularized. Okay. Now, instead of having 10 features, we have 1,000 features, and this low regularized linear model has now exploded. It's just not working at all. So this is trying to convey what we talk about in terms of this no free lunch theorem. You might have heard about it, and it seems like kind of a wacky idea that, oh, of course neural networks are better than linear models, or of course, like, my personal favorite thing is going to be better than the other thing. It turns out that you can mathematically prove that that's never the case. So you are going to have to experiment for each of your data sets. And oftentimes you actually can't take a ton of information about your previous knowledge or previous data sets into the future. There are some cases, and I'll talk about it right at the end of the talk, but that's mostly the issue here. All right, so the way that I visualize hyperparameters is I'm playing a really big synth. Got a nice old synth here with lots of knobs that I have no idea what they do, and a keyboard. And what you're trying to imagine is, okay, well, I do not know how to play the synth, but I've been told I need to recreate some song, right? Your favorite Diplo song or something like that. You start flipping some switches, and you notice that some of the switches that you flip seem to affect other switches in ways that you can't really predict. Also, you can't really tell if you're doing good or bad, but you do have a blind DJ who is telling you, oh, no, that's good, oh, that's bad. Right? So there's no sense of direction. You just have a single point, and you try to predict, okay, how well are things going to do overall? So why am I talking about this? Obviously, this is my idea of what hyperparameter tuning is. So it's a very difficult problem because you don't have that sense of direction that you would get. Hey, what's up?
I just wanted to ask this. I love this analogy. It takes a while after you press a note. It takes a while for the sound to come up.
Yeah, and we could also say that. Let's just go ahead and say, like, oh, you're doing it, and every time that you press onto press a different button here, you are going to have to pay a certain amount of money. And now it's a piano, because all of this stuff is going to take a lot of time, and it is going to be expensive in terms of compute. All right. So what can we learn about this? First of all, this is going to be really frustrating to do by hand, right? We're not getting a lot of feedback. It's going to take a long time. Overall, it's just kind of a crappy situation to be in. So that's kind of the motivation to figure out this hyperparameter optimization. Okay, so the combination of all hyperparameters is called hyperparameter space. This is different from parameter space, if you've heard about that. You see a lot of, if you look at a lot of neural network papers, they'll talk about parameter space and optimizing, and you'll see nice kind of smooth gradients and stuff like that. Hyperparameter space is much more deadly. So we know a few things about hyperparameter space. One, it's very, very large. It's huge. It's many dimensional, and it is as many dimensions as you want to optimize for. So it's relatively easy to, if we go back to our original example, optimize for that single regularization strength. But when you have regularization strength, but also what ratio should those regularizations be, whether it's L1 or L2, and then also we're asking about, I don't know, say robustness and stuff like that, then it's going to get more complicated. The other thing that we know is it's costly to explore, because the only way that you can actually evaluate it is to train a whole model and then do the prediction. And oftentimes you're not only just training the whole model, you'll be doing cross-validation for reasons I'll explain later. So that means you're training many different mini models of the same thing and getting an average out of that. It's not smooth, so you can't expect to take the grain out of hyperparameter space. It's kind of hard to explain just how much of a pain that is. If we could do this, this would not be a very difficult problem. We have a ton of different iterative methods, such as a stochastic gradient descent, that do a pretty decent job, but we just can't do it. Let's see, not all dimensions are equal. So we can think about certain things. Well, here's like a trivial case. The seed that you put into any stochastic algorithm really probably won't affect much at all, to the point where I wouldn't count it as a hyperparameter. But there are going to be other cases, like for instance in a neural network, where maybe the number of dense nodes in the fifth layer doesn't matter at all, because it turns out you only really ever needed 4, stuff like that. But it depends on the data set again. So because of those four reasons, it's really, really hard for humans to actually do this. There's not a lot of analogy that you can bring in, and even very experienced data scientists can end up spending a lot of time trying to tune these parameters. So all the kind of 1s, 2s, they're all references to different papers. There's been a lot of really great work done on this in a relatively quiet field. And I mostly quote a guy, I think Bergestra, hopefully I got his name right. And what he found was that, contrary to what you would expect, randomized search actually does a pretty good job. So if you don't want to do all the stuff that I'm going to talk about immediately after this, just remember that randomized search is actually probably going to do pretty great. Inside of the original the scikit-learn library, you have the option for grid search, which essentially just means take your hyperparameter space and find the little dots for all the different dimensions, and then evaluate each one of those. And randomized search, which literally is what it says, just pick completely randomly, don't learn anything ever. It turns out that randomized search almost always beats grid search, and it often beats hand tuning for a similar amount of time. And the reason why that is because of that fact that a lot of these dimensions don't actually matter, and it's really hard for you to tell actually if they do or not. All right. Any questions right now? All right, cool. Okay, just before I get into actually showing what this Hyperopt-Sklearn thing is, I wrote this part right at the end because I was thinking about it a lot. So every weekday for 2 weeks, so that's 10 days, I send you an email predicting whether or not the Dow Jones index will rise or fall, right? And I'm right every single time. Assuming that the Dow Jones index is independent of the past and equally likely to rise or fall, that's about 1 in 1,000. So that's pretty good. Is there anything that you need to know before you should give me all of your money? Does anyone want to guess?
What you're basing your guess on?
No. Well, yeah, I guess so. That's fair, but not what I was looking for. Yeah.
How many people you've emailed?
Yes, exactly. So, what if I send 10,000 random emails to people? Well, it turns out that we can show mathematically. This is you can grab this out of the NumPy random library, and this is a little binomial, just success failure kind of distribution. If I send out 10,000 emails, you were one of the 9 people that got everything perfect, right? So why am I talking about this? There is a problem that I don't think that data scientists talk about enough called optimization bias, where essentially you could imagine that instead of me being the emailer sending you whether or not Dow Jones is going to go up or down, you have this algorithm that is making many, many models, right? So instead of me sending out 10,000 emails, I'm now making 10,000 models, right? So now we have a very small validation set. So it turns out that I get a lot of things that look like really, really good. But the problem is, as soon as you put them into production, they just completely fail. So in this analogy, putting all your money, giving me all your money is the same as putting a really crappy model into production, because you just might lose your job. All right. So how do we actually defeat this optimization bias, which is really just trying a bunch of things and only reporting the best thing? The answer is always get more data, the best kind of data that you can get. As you get more data, your data is going to approximate the distributions of what's actually going on in your latent process a lot better. But the thing that you can actually deal with, because often data is hard to get or expensive, is cross-validation. And I didn't put in a reference here, but you probably have heard about elements of statistical learning. And my favorite chapter is on cross-validation, because they really go into exactly why this is better than just doing a leave-out set for validation. And essentially what's happening is your cross-validation, training a bunch of different little models, right? And then you're averaging, and it turns out that you actually get a lower amount of measurement error between validation and test. But the other thing you need to do is build fewer models. So if I sent you, if I only sent out 10 emails, and it turns out that one of them got all 10 days correct, that's actually still quite good. So you just need to be thinking about how many models that you make, and eventually it's really, I find that this stuff is actually kind of addictive, because it just makes the numbers go up and you don't have to do a ton of work. But you are going to have to stop. So you need to kind of set out for yourself the amount of time or models that you're going to make, and then stop after that and don't continue. What's up?
So I've been thinking about this lately. So I mean, if I'm cross-validating, I still have optimization bias.
Yes, but it grows slower.
Yeah. Do you have any sense, like orders of magnitude here? Like.
So it's proportional to the number of folds you have up to a certain point, where in that ESL chapter they say about 10 times cross-validation is about the max that you're going to go, and then it just plateaus. One thing that you can do, and this is actually my contribution to this Hyperopt-Sklearn package, is to use repeated cross-fold validation. And that means take different seeds and then repeat cross-validation multiple times. Essentially what you're trying to do is you're trying to make sure that there's been no memorization going on, and that this model works in many, many different circumstances. Right?
Not just cherry picking.
Not just cherry picking.
But like when I'm doing like multiple cross-fold, the cost is growing. Like,
yes.
I mean linearly, but still.
So you're paying in time.
Yeah.
Right. So there'll come a point where maybe you have 600 gigs or terabytes or whatever big data is now of data. Cross-validation probably isn't going to be your thing, because you have so much data that hopefully it washes out, and you just can't spend months waiting for this model to come up unless you're Google or something like that. So we tend to work in my company on small to medium-ish data. So I do repeated cross-fold validation whenever I can, just because that little bit of extra, I just want that reassurance, right? That we're getting relatively close to what the test accuracy is actually going to be. Anything else about that? All right.
But you wouldn't go so far as like leave one out. Like
so
10 folds is good enough.
So interesting in the chapter asked about leave one out. Sorry, blue ball. Leave one out actually doesn't work as well as you would think it does. It turns out that it actually does hit this sort of wall and becomes, I think, biased in some way. I'm trying to remember exactly if it's up or down. But yeah, leave one out is almost never the answer. You should probably just be repeating your 5-fold or your 10-fold instead of doing leave one out, unless you have a really good reason to. All right. Yeah, so as mentioned before, hyperparameter optimization is computationally costly. And if you're doing it by hand, it's also really costly for your company, because you're spending all of this time just pressing a button and waiting, right? Yeah. Also, what's going to happen is your ideal hyperparameters are going to change depending on your feature engineering. And generally what I would suggest, and this is just kind of a word to the wise here, is don't do this until right at the end, when you think that your model is pretty much ready to go and you're sending it off and it's going to be in production. Because what you'll find is you'll be doing this, and then something changes about your data. Maybe you find a bug, or you want to add another feature, and then you try the exact same model you had, only with one more feature or one feature slightly changed, and it's just not as good as it was. So it's a lot of wasted time. I like to think of doing this hyperparameter tuning is kind of like laminating a model, where you're saying, hey, this thing it's buffed up, it's ready to go. I'm sending it out. What are the last little bits of predictiveness that I can juice out of here? All right. Okay, so dessert first. I want to show you what Hyperopt-Sklearn does, and then I'll go ahead and explain like what the math is, right? Because the math isn't super fun, but I think this is a pretty neat package, and no one's talking about it. Okay, so just introduction to the data. We have MNIST, and this is the scikit-learn MNIST, which has been downsampled. So you're looking at trying to recognize handwriting based off of different values in an array, which can be shaped like an image. And this is supposed to be an 8. So you can see that it's not always the best kind of approximation of what people actually write like. So I just take a random forest classifier. It's one of the things that I like to try first. And I already do pretty well on this. I get a 95% accuracy. So I'm only getting about 1 in 20 images wrong. Just a quick note, look up scikit-plot, which I think is just like a really great package. It has a bunch of built-in, basically everything where you look at the scikit-learn documentation, and it's like, oh, that's a really nice plot of a confusion matrix, or a classification report, scree plot, whatever. This has it built in, and it's just super simple to use. All right. So yeah, you can see that it's getting some stuff wrong here where it's predicting a 9, but it's actually a 3. Okay, but good baseline. So this is literally everything you need to do in order to actually get Hyperopt-Sklearn to work. You import it, you fit it, and then you make a model. So make sure to save this model. This took me about 30 minutes to train. And then, boom. It's now at 99% accuracy, so that's 1 out of 100 wrong. And it chooses something that, if you looked at MNIST before, makes a lot of sense. It's a k nearest neighbors, so it's just looking at, what is this closest to? Yeah, and that's it. Like literally, you can do this on tons of problems. I've done this on Kaggle problems and stuff like that. I should go back and show. So you can choose the number of folds for your Hyperopt model when it's fitting, and what gets produced here we'll kind of get into a little bit more. But it's essentially just the history of all the models that were trained in this amount of time. I did 100 evaluations here, and I said any classifier will do. I don't care whether it's a linear model. It's got XGBoost and light GBM as well, so it's not just scikit-learn models. And you could theoretically put in anything that has a scikit-learn compatible API. So yeah, and it really is that simple. What's up?
So when you did the Hyperopt thing, when you said 99% accuracy, nearest neighbors are known to overfit.
Yeah. Well, this is on test.
Yeah, but the thing is it a cross-validated average of 5 folds, or is it?
So the test accuracy here is not. It is. So essentially, what I did was I took out the one test, right? So that was about 25%, I believe, and then did cross-validation for the actual model itself. So yeah, there is still a possibility of overfitting in this case as well. I just figured because the model has only seen this data once in its entirety, you actually don't have any optimization bias. I should say that if I were to send you an email and you were the only recipient of the email, and I get it right 10 times in a row, you really should give me all your money. What's up?
So what it found in the winning model,
yeah.
Did all of those parameters come from its hyperparameter search?
Yeah, so it chose the model. I don't believe it chose algorithm or number of jobs, but this P here, number of neighbors, leaf size, the metric, I believe all of those were picked. Another nice thing that it does is it actually also picks preprocessors as well. So it does normalization. It can also do a PCA or a min-max scaler. Kenneth?
Yeah, can you just go on the side of the API, maybe kind of classify as
You can, and I'll show you how to add that to the to this any classifier that was used. So any classifier, you'll have to make your own version of this, essentially defining the hyperparameter space. But yeah, that you can add anything that has that. Of course.
You mentioned about like using this hyperparameter optimization tools and the workflow.
Yeah.
Is there any use or using it at the start of the workflow? You are actually trying to get ideas about, hey, potentially what's the load maximum, what kind of model I want to use, which direction I want to go.
Perfect. Haha. Yes. So what we have here is we have the 100 different 100 different models that have been trained, and you can get information on absolutely everything that was used to train the model. But here I'm just looking at the different types of models that were tried. Right here is K&N's. Basically everything that K&N did was really good. You can look at this support vector classifier, which everything is really amazing except for this one dot down here. I don't know exactly what happened here. It might have been a failure or something like that. But this kind of gives you an idea of the whole area. But I would give the caveat that perhaps what would be better to do would just be run one random forest, one XGBoost, one etc., and see where you are, give a kind of a brief idea of what's going on here, and then go on and play with your models a little bit more, and play with your data. Just because of the optimization bias. I found that this package it's very fun to play with, right? Because it just keeps on saying like, hey, you're doing better, you're doing better, you're doing better, right? It's got that kind of Pavlovian response. But often I would find myself just looking at the thing instead of doing real work, right? So I would suggest that you don't do this till the end. This truly is the dessert of building models, I feel, because this is where all of the the nice numbers, everything that you've been trained in Kaggle to do, this is where it all comes out. Anything else? So one thing that you kind of don't see from this example, because it's relatively simple, this is just the validation or cross-validation loss over time. If this were a harder problem, what you would see is the accuracy slowly increasing over time. So unlike randomized search, this kind of search actually does do some learning, and I'll be talking about exactly how it does learning in a little bit. But yeah, what's great about this is you can actually be running this for a lot longer and get something that is going to be better. Okay, and how that happens is in the next slide, and this is where I get into algorithms and math and stuff like that. So here we go. Okay, sequential model-based optimization. This is kind of the overarching idea behind any kind of hyperparameter optimization where you try to learn something about the distribution. Yep.
Do you compare your package with the other existing package for the optimization, like the Sklearn optimize or AutoML? So there are so many packages available right now. Have you ever compared the results of your packages with other packages?
I haven't, but there was a paper about this. And generally, what we see is and I actually should say that this field is rapidly evolving. It's kind of caught fire. The algorithm that I'm going to show is from a paper from 2013, and it kind of just languished there for a while. And now I think all the big companies are realizing like we could save a lot of money if we just figure out how to do this better. So we're seeing a lot of papers, even in the last couple of weeks and months. But yes, during the essentially what they did was they trained on many, many data sets, and they looked at what we'll be talking about, which is called tree parsean estimators. Gaussian processes is the other kind of classic way of doing this. And then random search as the baseline. And then very recently, it was kind of cheeky of someone to do random search, but using 2 computers instead of 1. And it turns out using 2 computers instead of 1 is actually a really good idea. And the nice thing about that is, if you're completely random, being parallel is very, very simple, right? Because you just run the same algorithm twice, and you don't care about the computers talking to each other. Yeah, so, right. Sequential model-based optimization. This is how you learn your hyperparameters. So you start out, you need to make a container for all the data that you're going to keep. And then for each time step, so one thing to know is you actually have to say the amount of time steps that you have. And in the case that we're looking at, it's the number of models that you create. You can also, not with this package, but with other packages, you can actually just say, I want this to run for 8 hours, and at the end of the 8 hours, I want you to tell me what's best. So for each time step and the total number of time steps, find the most promising set of hyperparameters based off of a surrogate function and a model for your data. So that's actually the key part of this right here, is we know that trying all of these different models, right, is really, really expensive, right? So we need something cheaper, and we need to find the best kind of cheap thing, and then what we'll do is we'll confirm how well our model, our cheap function, is actually doing by trying it on our real expensive function, right? So we're trying to actually get a sense for the data, a sense for, you know, this evaluation metric, and then we end up actually testing it. So we update our history with this new information about the one point that has been sampled from the very expensive hyperparameter space that was probably selected out of maybe 10,000 samples of the very easy to sample space. And then we update the model of the data given the new history. Yeah.
What's the difference between this one and the Bayesian optimization?
This is Bayesian optimization. So this is all of the methods. For Bayes optimization, people tend to say, like Gaussian processes, like when you look at Bayes opt and Spearmint and stuff like that, it's all Gaussian process based. This is also Bayesian. I can prove it to you because we actually have to use Bayes' theorem in order to get something that we want. But yes, why we use Bayesian optimization is because Bayes is quite good at getting information about, you know, distributions based off of very little data. Yes?
Might be a dumb question, but where do you specify the ranges of the parameters?
Yeah, so that model of the data is where we'll specify that. This is very general, so we haven't even done that yet. And it turns out the different kind of flavors of SMBO, you make different kind of assumptions. So in Gaussian processes, you just give a min and a max. In what I'll be doing called TPE, you actually give like a prior distribution, which will normally be like a normal or a log normal or a uniform, something like that. Anything else? All right. Right. So how should we model the data? This is just, if you want to hear about Gaussian processes, tell me, and I'll do a talk on Gaussian processes later, but not today.
You just said you need a prior distribution for the, so how do you understand the prior distribution?
Yeah, so in this case, this is like the core of the talk. So very astute question, we'll get to it. Yeah, it turns out that it doesn't terribly matter if we run this for long enough, but yeah.
But my other question is, can you specify that how you want to use only, say, GBM or XGBoost, both?
Yep. Yeah, you can, and that comes down to actually specifying the hyperparameter space itself. Okay. I can also say, like, say you want to use like a SVM, but you only want to use a certain type of kernel, right? That's also possible. You can make things conditional, and you can say that certain things are not allowed and certain things are allowed. Okay. All right, math time. So a surrogate function is put forward for like the best proposal for the actual function. And that's a little bit garbled. So there were actually, in this original paper, which I believe is from 2011. I should say, actually, this is kind of funny. A lot of talk that I've seen online about hyperparameter optimization, just like everything else, it gets super tribal. And I've seen people be like, "Oh, Gaussian processes is the best thing in the world, and if you're using TPE, you're an idiot." So the same guy proposed both of these algorithms in the same paper, and they have positives and negatives. It's really hard to actually say definitely which one is better than the other. Again, no free lunch. What they generally found, though, is if you think that your hyperparameter space has a lot of those hyperparameters that aren't going to matter a ton, so this is probably going to matter a lot in neural networks and stuff like that, this tends to do better, because it eventually just kind of learns that nothing is really working, so we're just going to sample randomly until otherwise. By randomly, I mean uniformly. But yeah, Gaussian processes is totally fine to do as well. Okay, in this original paper, they talk about expected improvement, which is it's an expectation type of equation where you have some sort of threshold and you're trying to figure out, okay, what hyperparameters can I have to predict y, and how do I make sure that y is better than some, or less than, I guess in this case, y star, which is some threshold. The reason why it's written like this and not the other way around is because all of these models are trying to minimize a loss function instead of maximize. You can just multiply everything by -1 to switch it around. In this case, essentially what we're doing, and we'll talk about, let's do this instead. Okay, so what is the core of this TPE algorithm, right? Essentially all that you're doing is you're creating two distributions. One distribution is your distribution of every single, essentially you have your good distribution and your bad distribution. And then you look at the values in your good like a value, and you're looking at, okay, how probable is this value in your good distribution? So a distribution that has generally led to a good result, and how often does it occur in this poor distribution, right? You look at the ratio between the two, and if something appears in the good ratio, or sorry, the good distribution a bunch, but not very often in the poor distribution, then you should just select that over and over again. And I'm actually just going to draw this right now. So this is good. Nope. Okay. Let's do this.
Oh, that's
yeah. Okay. Good. It's good.
Oh yeah, sure. I hate you, man.
Right? And you can imagine superimposing these. So what you want to sample is basically from these two peaks, and you never want to sample from here, right? And that's how you get essentially like a different ratio. Okay.
Matt,
yes.
So what is good and bad?
Yes.
So is it in terms of the results, and this is the distribution? So what's on the x-axis?
Yes. Okay. So yes, the way that we define goodness is we look at the previous history, and we say, okay, everything that so for the default value, everything that is in the top 15% of results. So if, for example, we're trying to get accuracy, and for k nearest neighbors, it turns out that 3, 4, and 5 nearest neighbors all appear in the top 10% or top 15% of the models that we've tried, but 30 nearest neighbors only appears in the poor distribution, then we should just be sampling 3, 4, and 5. Like we've learned that those parameters do best. Does that make sense? Yes.
Is this so? Do you have one for each of the classifiers that you end up training?
So you have one for each hyperparameter, including conditional hyperparameters. And what you can do is when you're conditioning on, so I'm going to keep on going to SVM. So you have a kernel and then maybe kernel width. You want that to be different for your different kernels. So you can have conditional distributions as well, where maybe a width of 1 is very good in the linear case, but very bad in a different case. But yeah. So one thing to note is now we're talking about the hyperparameters conditioned on how well it did in the past, right? So we have the inverse probability of what we had before, right? We had p y conditioned on x, right? Which kind of makes sense. We're trying to figure out, can we predict what we're going to get based off of the hyperparameters. What we have instead here is the inverse. All right, moved around. So I didn't go into the derivation, but essentially you can prove using Bayes' theorem that this is totally fine, and because we're only looking at whether or not something is increasing or not, we don't have to worry about the nasty denominator of the Bayes rule. Also, we have these weird distributions right here, L and G. L probably means less than, and G is probably greater than, but it's never really elucidated in the original paper. Talking about Y star, it's a hyperparameter. So just to kind of get that into your head, it's a modeling assumption you're making about the model that is creating all the other models, right? I don't think it matters a ton. You're just looking at ratios and stuff like that. But maybe you find something that is just not right. You can go ahead and change this. Inside of the TPE algorithm itself, it's actually defined as gamma, which is just going to be like, in this case, like 0.15. So the probability that y is going to be less than y star. Okay, this part right here is the most complicated and weird and just doesn't make a ton of sense part. If you have any questions, this is definitely the time to ask.
So what's the distribution of the y?
Yes. The distribution of the y, we don't really know, right? If we knew the distributions of y's, then we should be able to solve the problem already, right? We know the distribution of y given x in kind of a sort of case, but this is not really, I guess. Yeah. No. What's up?
Is there some assumption about the smoothness of that distribution? Like if it looked like white noise, then maybe we couldn't do much with it.
So, not really. It turns out that you can do this for discrete probabilities and continuous probabilities, but what happens is instead of having distribution that's really easy to show the parameters for, you have this non-parametric distribution, which is just kind of like a fancy way of saying it's just a bunch of mixture of Gaussians, so you add a bunch of Gaussians together, and that's kind of the next thing that we'll be talking about. But yeah, there's no assumption about smoothings.
What's Y?
Sorry?
What is
Y is your validation or cross-validation performance, right? So in the case of MNIST, our Y would have been cross-validation accuracy.
Does 50% mean 85% validation accuracy?
Yeah, it means we have a no. Okay. Perfect. Great. Yes. Sorry, everyone. Okay. If we have an accuracy should be larger. So in the case you would just multiply by -1, but let's go with larger here. So you get an this is going over here. Okay, you have an accuracy. You get 0.5% accuracy. That's bad. You get 0.2. You get a 0.5. So you get a 0.8, and then a 0.9, right? So you're trying to look for. If I did more of this, let's say that we're looking at like y star, the 0.2. We're essentially looking at quantiles here. So we want the hyperparameters that gave us the 0.9, right? And as we keep on adding numbers into this history, right, it's going to get bigger and bigger, right? So 0.1, this is bad. You get 0.95, that's great. And then this and crappy again. Right. So now we say, okay, what were the hyperparameters that gave us 0.95 and 0.9, right? And then we use that information to create like these distributions, and we're trying to sample from these, but trying not to sample from these so much. So it's relative to how well you're doing at the current moment.
So that pointer is 20 percentile?
Yeah, this was like 20 percentile, right? But again, 15 percentile is how it starts. Yep, Kenneth?
So you don't need to sample on the bad distributions because you already have the good distribution.
So essentially, what this thing is trying to do overall is it's actually trying to predict whether or not the sample that it was given is a good or bad, is sampled from the good or bad distributions, right? And its way of expressing belief in that is by this ratio of good over bad.
It sounds like you're modeling them independently.
Yes. Yeah, so that is one thing that is a little bit crazy, I know.
Right.
The problem is, as soon as we start looking at, so one, we can embed conditionals in certain cases, right? So obviously it doesn't make sense to model the number of nearest neighbors if you're running an XGBoost, right? So that's possible. But yes, this is a very naive assumption to make, right? But
which you wouldn't make in Gaussian processes.
Right. But the problem with Gaussian processes is you're going to have the case where you're trying to predict, oh, what's the best way of modeling this in this hyperparameter that isn't very informative. And the time that you spent trying to model the thing that isn't very informative doesn't really matter here, because this model automatically starts going like, oh, it doesn't matter? Well, then I'm not going to spend any time trying to optimize that kind of area. But yes, that is the advantage, like the advantage of Gaussian processes over this algorithm. I guess there's the other one is Gaussian processes just makes like intuitive sense in this kind of case, right? Like, you know, you're trying to model this kind of space, and Gaussian processes will do a great job of it. Yes?
Is there a defined range for y?
For y, it's up to you,
okay.
right? So if it is, say, mean absolute error, right? Your range is 0 to unbounded, but if it's accuracy, it's 0 to 1. And it doesn't really matter because this quantile range, it doesn't really matter the scale of it.
What's going to be happening if the variance of the y is very, very small?
If it's very, very small, I can see how you could get like measurement errors at that point, but at that time, like, I'm not really sure if it's possible to do any better than this. Yeah.
I might have missed it, but where's the tree?
Oh, yeah, we'll get to that.
Oh.
Yeah. Anything else? All right. Yes?
Last question. So when you say you're taking ratios between something of the good distribution and the bad distribution,
yeah.
In some sense, are you trying to do a hypothesis test?
No. I'm going to say no, because this is like strictly a Bayesian idea, and I'm not sure you really want to say it's a hypothesis. And we're not really looking for significance, right? And you know, we're sampling many times, right? Yeah, I wouldn't count it as that. I think if you were to get to the end of this process and you've done it like 100 or 1,000 times, you might be able to actually look at these two like distributions and see if they are significantly different. But yeah, there's just no explicit significance testing. Anyone else?
On the topic of missing trees, I think I don't see any priors either.
Yeah, well, that's about to happen.
Okay.
Yeah. All right. Good. All right. So what are L and G? So they start out as some prior distribution. This is where you actually say what they are. Oh. Oops. Hi. So uniform. Basically all these priors, because they almost immediately get substituted for a Gaussian mixture of some kind. The priors are mostly there to set boundaries. So you know that if you're using a uniform, that there's going to be boundaries on the lower and the top half of something. So this might be, it's not regularization strength, but we could say something along the lines of some percentage. I can't think of a hyperparameter that is percentage based right now. Or what is it? It's in decision trees. It's the level of impurity that you're allowed to have in leaves. Log uniform, just take the log of that, so that gives you a bottom and a top still, but over a much greater range. Normal, which has no bounding. Log normal, which does have, you can't go below 0, and that one's actually used quite a bit if you think about it, like for, say, the number of trees in a random forest is going to be a log normal. And then discrete. So one of the nice things about this is you can also directly model discrete variables as well. So if the prior is continuous, you just take that prior distribution and you throw it out. So I'm not sure if you really call it a prior, but they called it a prior when they were writing about it. And they turned it into a 1D, a Gaussian mixture, and they also called it truncated. So there's a point where it just gets clipped, but that's not super important. Sorry?
You're hiding.
Oh, of course. Sorry. Hi. So if it's discrete, though, you're just kind of like adding weight onto like the things that are good or bad. So, hi. So you start out with everything the same, right? And so this could be something like, let's say, do something like. So there's Gini cuts and there's entropy cuts. And this isn't important, this is an example, right? So inside of a decision tree, you have to choose how you're going to cut, how you're going to decide what each node is going to be. And you have two examples in scikit-learn, is this Gini coefficient and the entropy. And if it turns out that entropy does better, you just add a little bit on top and you take away from Gini, right? You can also specify, like, not a priori, but you can specify maybe in the past, actually here's a better example. So the type of model that you use, if you suspect that a random forest is going to do better, you can actually give a little bit of a boost right when you start. You can say, with 0.6 probability, I think that this is going to be a random forest, and it'll eventually correct if it turns out random forest is not a great model for your data. Does that make sense? Okay. All right. Okay, here's the thing that it's actually optimizing if you care about the math. Again, this gamma. This gamma is the proportion that you want to be in the winning or the, I guess the good distribution. Yeah, that's about it. I don't want to talk about this anymore. It's essentially very easy to sample from this. Gaussian mixtures are very easy to make and then sample from, right? I even, in the previous version of this talk, I went through and showed what that's like. Okay, but what if you don't know what a Gaussian mixture is? Okay, so this is how your priors or how your distributions are actually being constructed. And as far as I can tell, I haven't seen anyone actually talk about this except for the paper where this was written. So you're sampling, and you pick out your best sample, right? And you go into your next iteration. So now what's going to happen is that thing that you sampled, let's say it's regularization strength, just so we have something concrete, that becomes the mean of a new Gaussian distribution, and the standard deviation is the greater of the distance between its two neighbors, right? So if you have 0.01 is the thing that you sampled, and then 0.02 is one neighbor, but 0.05 is the neighbor that's like smaller than it. You choose the distance between 0.01 and 0.02, so that's going to be your standard deviation. So what you'll get is a whole bunch of little Gaussians that'll look like this, where the variances will get, or the standard deviations will get smaller and smaller over time, generally, right? Because you'll have more and more samples. So it kind of smooths things out. When you start, it's going to be like really, really sharp, and then as you sample more and more, you're going to get kind of like a bumpy road, right? But if you find something that just, it never works for you, it's going to drop close to 0, which is nice. And that's really what you want, is you want to find values that just kind of never work for you. Questions about that? All right, cool. Great. So we're out of Mathland. This is awesome. What is Hyperopt? What's?
Maybe before you jump.
Yes, please.
So you can answer this in a hand-wavy way. It might just help me understand.
Will do.
Say I use this and it takes 8 hours and I get a bunch of optimal, good hyperparameters, but for some reason I'm not confident and I just say, oh, what the hell, I'm going to run it another 8 hours when I just run it again from the beginning. Why is that going to be worse than if at the beginning I just said, look, I'm going to do this for 16 hours and take the parameters at the end?
Okay, good news. If you stop it, you can actually restart it.
Okay.
Yeah, but to your point, essentially what we're having, if we can think about that discrete case again, if we have already determined that there is just like a certain option, let's say that in the case that we're looking at, there's just no way to make naive Bayes work in this case. Every time that you sample naive Bayes is essentially like wasted for you, right? Because you know that it's going to be pretty bad. So by continuing on doing the 16 hours instead of the 8 hours, right, you start learning a little bit more about like what the data needs out of your models. Right? That's at least the intuition for it. Make sense?
Yeah. Is it enough to say it just explores more of the space that it hasn't explored yet and potentially finds a better value?
Well, it will tend to explore. So here's the thing, and this is you bring up a great point. This is the classic explore exploit problem. Do you want to explore close by something that has already worked really well, or do you want to explore some place that's way far off where you don't have a good understanding of what the shape is? And this is where Gaussian processes does a really great job. What will tend to happen is as you just naturally go through this point and you start making distributions that are centering around certain areas, you want to be exploring that, because if you think about it, that's only in one dimension. If you think about it in like 30 dimensions, right? You want to be looking at combinations that already look pretty promising, but we haven't like run all the permutations for it, right? Like we want to look at, let's say, for example, the thing in Hyperopt-Sklearn that we got out was k nearest neighbors with 3 neighbors, right? Okay, what distance metric works best for these 3 neighbors? Because it's probably that the 3 neighbors, that's probably a very important hyperparameter. So we want to focus on that area, but those other kind of less important hyperparameters, that's what gets optimized as we go forward, because it's already decided that 3, 4, 5 is a really good number for our data. Anyone else? All right. So Hyperopt was not originally meant to be just the reference implementation of this TPE, tree-based parser estimators. Oh, I should say what is tree-based. Okay, here we go. It's because it's conditional, right? So you're making like a decision about, say, it's going to be a decision tree, and then you have to choose max depth. It's represented as a tree. That's essentially it. So it was trying to highlight that you can have conditional distributions. But yeah, it's very basically tree-based. Okay. So yeah, Hyperopt is also a general framework for optimizing. So you could theoretically put in your own algorithm. We'll see like where you would put that in, and ask it to minimize, and it'll do just as fine as if it were Gaussian processes or whatever crazy idea that you came up with. So to use Hyperopt, this is Hyperopt, not Hyperopt-Sklearn, which is the thing that we looked at, feels like a million years ago. This is a general purpose library that you can use on stuff like neural networks that don't have a very easy scikit-learn wrapper to it. You need a function to minimize, so it's almost always going to be make a model and then look at cross-validation or whatever. Assess that model. Make the model assess it. You want your hyperparameter space, and I'm going to show you how to actually define a hyperparameter space. You need that object to store our experiments in. Something called trials, which is basically just a dictionary with some fancy stuff attached to it, and then your search algorithm, and it's going to be TPE probably, because I just spent so much time explaining what TPE is. So here's our function here. This is going all the way back to MNIST again, and I'm just showing essentially what this function is. It doesn't really matter for right now, but if you look at my code, which will be or is already available online for free, and you're trying to figure out how to actually run this, I think I've seen one blog post that actually does this from scratch. So if you're looking for a reference on like how to actually set it up, like look at this stuff. So I have a cross-validation going here. I have the space arguments, which is just the argument, and I'll show you what that looks like. Train X and train Y are going to be these MNest, so the parameters or the data, and then what you're estimating, and then accuracy score, which is going all the way over here. And then what you want to return is your results, so just the cross-validated results, and the status. And this is just to kind of show what's going on. You want to include this because if you don't include this, and you do hit an exception, which is very possible because this algorithm doesn't know stuff very well, and if you misspecify some sort of hyperparameter space, say choose like a negative number of trees, it's going to do that, and eventually it's going to hit that negative thing, and in the middle of the night it's going to say, hey, this thing doesn't exist, and I'm just going to fail. So instead you just capture that exception and make sure that you send the exception back to outside of this experiment. All right. Okay, here's the more important part. This right here is a whole lot of code and kind of dense. But essentially what you have right here is you're defining the scope of something. So this is where you can get something conditional. So I'm saying that k nearest neighbors classifier, we should be, whatever goes inside of that function is now conditional being inside of that function. So we need to do that, otherwise we're going to start sampling the nearest neighbors for a random forest, which doesn't make sense, and then we're going to start sampling the split criteria in nearest neighbors, and you're going to get an error. It's going to be bad. So this is just showing that you can do stuff like you can weight different ways. So we know that k nearest neighbors is probably going to be pretty good, so we gave it 60% chance of sampling. What's up?
Is it smart about the failures? Like, does it figure out, oh, this range seems to be all failures, so I'm going to avoid that range?
Yes. I'm trying to remember how it does that, though. Okay. But it does tend to avoid, I don't think it counts it as like infinite loss, but it will, actually I'm not sure if that's true. I'll go check for you. But in my kind of empirical experience, it seems to have less bad combinations over time. The other thing that you can do in, I believe, Hyperopt-Sklearn is set the amount of time that you want for a model. So if something does decently well, but it's orders of magnitude more expensive, time-wise, then you can say, hey, this is actually a failure because we can't wait, an hour to get a result. We need it in 30 seconds. Yeah, so you can specify the choices. So you have your discrete variables, you have your continuous variables. Here you have this nice log uniform thing, and this Q just means that turn that into like an integer. So between 10 and 3,000 random forest. Okay. Right. And this is just the function that actually do the minimizing. So it's called fmin, function minimize. We have TPE suggest, which is the algorithm that we just went through. The number of evaluations, this trials object, which we'll see in just a second. And I ran it for 10, and it gave us the same results as Hyperopt-Sklearn. So that's kind of fun. It doesn't have all of the other special stuff about that Minkowski distance or whatever. But yeah, we got 3 nearest neighbors, so it turns out that's actually probably pretty smart to have. Okay, so basically why Hyperopt-Sklearn? We're just in the stretch where I just kind of bring it all together. What's beautiful about Hyperopt-Sklearn is you don't have to do this. This sucks. It really sucks to write this. I spent more time than you would expect trying to get this to work because the documentation isn't great on this. And to be honest, I'm just not enough of an expert to really think, okay, what is the minimum and the maximum number of trees that I should expect to do well in a random forest? So instead we had a bunch of people, so Yoshua Bengio and James Bergeistra, who wrote this original algorithm, I believe actually specified this hyperparameter space for us, which is very nice. And as far as I can tell, the assumptions that they made are pretty smart. So it wraps around the Scikit-Learn API, which is great, right? Everyone kind of understands how that works. Supports XGBoost. I should also say the Microsoft version of that, whatever it's called. I just lost my train of thought there. Reasonable prior distributions. Also, I fixed a whole bunch of stuff in it. So you should use my version instead of the reference version, because as far as I can tell, Bergeistra is now like the CTO of a company in Eastern Canada, and is probably doing very important tech stuff and doesn't have time to answer all of my issues.
How many?
A couple, and then eventually I was like, I should actually, be the change in the world I want to see, right? And fix the things. So yeah, this is Python 3 compatible and stuff like that. I do not want to insult him because he seems like a very smart man, and it's amazing that he actually wrote all of this stuff. So thank you for doing this. Also, I've made a few notes on the margin. Okay, things that I didn't really mention. What's up?
What was that diagram?
Oh yeah, sorry. I just kind of this is the tree part of the tree-based estimator. So you specify a model, a preprocessor, and a classifier. This comes from the the Hyperopt-Sklearn paper, which is a really easy read if you're interested. But there isn't a ton that you do not already know. Essentially, what it's saying is, okay, make a choice about processing, including none. Okay, it chose a PCA. Make a new tree, and here's the hyperparameters for PCA that we're going to sample. We choose the number of components, that's important, and we choose this Boolean of whether or not we need to whiten the PCA. Okay, after that's done, go back to the classifier, some sort of classification process. KNN, that's great. Choose the number of neighbors. Oh, 3. That's actually kind of funny. I didn't even realize that this was that it was also 3K nearest neighbors. You have your weights, you have your leaf size, and you have the algorithm that decides what the algorithm that decides what distance is going to be. Okay. Yeah. Yeah.
The pre-processing is not necessarily mutually exclusive of your classifier.
Yeah, in this case it is. I'll go talk about a different library where you can actually have multiple pre-processings. Also, one thing that isn't here is imputation. So that should be put in before. The problem is, by doing your imputation before you do the cross-validation, you are now introducing some level of data leakage into your experiment, which is a problem.
What is this topic point?
Sorry?
What is this topic point for the algorithm? That this is the best combination of the hyperparameter.
It stops when you tell it to stop, essentially. So you say train 100 models, and then after 100 models, it'll come back. Now you can also, you can interrupt it, and it will return back to you a trials object, but not like a finished thing, and you can start it again. But yeah, it's kind of work. What I would do is I would run it a couple times, maybe 2 or 3, just to see that it was actually like working as you expected, and then I would run it for a very long time, basically overnight or something like that. That's when I tend to do this thing. It's like, okay, build a model that I think is pretty sweet. Now I'm going to do all the fine tuning, and I'm going to do that at 5 p.m. so I don't have to look at it. So yeah.
Is there some way that you can tell it, I would prefer the model be fast to train? Like work that into the cost?
Yeah, so actually in the original paper they talk about that. And when it was in the paper, they said this is something that we'll be getting to soon. That was written in 2013. I'm not sure if they actually got to it. But what you could do is you could actually put that as your, when you go back here, what? Here, right? So instead of having accuracy results, it might be accuracy results plus some normalizing constant plus time, right? Or you have time here and time delta, right? So that could be possibly it too, but you're gonna have to be very careful about weighting the two cases. but you can also give it like a maximum of 30 seconds to train or something like that. Yeah. You have another question?
Yeah, I have a bunch.
Please go ahead. It's winding down, so.
Can you ask it afterwards, like, so what was significant and what wasn't? Like, what things just didn't really matter? Or, like, get it more of a sense of the space?
Yeah.
Aside from just the top?
Like,
examples?
So kind of not really. What you get back is only the best things that it thought, right? It doesn't have all the... When you go back all the way to that surrogate function, it discards everything except for the very best option, right?
Does it maintain that in the history somewhere that maybe you could dig for it?
It maintains only the best. It doesn't maintain all the things that it thinks were bad.
It doesn't maintain the bad distribution?
It must in some case. There must be a way of doing that because you can do warm starting, but I actually haven't seen it. So the thing about it is you'll get this very large dictionary, and it's kind of weird to explore. So I've done a fair amount of work. Well, finding like, okay, I did that thing where I showed which models did it select, right? I guess you could also infer if maybe in the back half something isn't selected, that's probably because it was found to be not very good. But I'm not sure how you take it, the distributions themselves out of it. It probably does exist, I just don't know how to get it. Yeah, go ahead.
Okay, so like in the DeepMind papers recently, they'll always, when they're looking at an algorithm, they'll do some kind of like analysis of the hyperparameters to say how sensitive is this algorithm to various hyperparameters. And then I think the reason for doing that is saying they want to produce algorithms that are robust and they work in large ranges. And if you make an algorithm that's just super sensitive to hyperparameters, then it's not in general. So I guess it's kind of like a different question that's being asked of the system is not find me the hyperparameters across these models, but it's more like given this model, find me how sensitive it is to the hyperparameters. Do you think this could be rejigged for that, or is that kind of a totally...
The way that I would do that is to return the variance of your cross-validation as well as your mean, right? So if you're doing a cross-validation, say 10-fold, and you have a decent result, but 2 of those results are just absolute garbage, right? And everything else is like really good. That could mean that it's not very robust. But if you get something that is like everything was very tight around the average, that might mean that it is more robust. But I haven't done any work on that, to be honest. Yeah. Anyone else? Yeah.
It's a bit related to that. So does it tell you whether it's done? Does it say, yeah, I'm done, or no, I really need more time to search for this?
It's never done. You could theoretically run this thing until the end of the time, and it will never say that it is done. It's only done when you say it's done.
You haven't given it enough time, or you've got too many hyperparameters. Would you know?
No. This is another classic problem. You just don't know when this thing converges and gets to the proper distributions. You just don't know. It's a hard problem.
Are you getting some feedback as it goes to see, oh, it's still going up, it's still going up?
Or yeah, you can get that feedback, but it's
might give you a hint.
Yeah, basically if there hasn't been like an increase in a long period of time, like it's probably done, right? There's actually an extension onto this, something called Hyperband, which reformulates this as a bandit problem, which I can't really get into right now. But essentially what it says is, let's give it 8 hours. At 4 hours, let's say everything that is not in the top X%, never sample again. Make it smaller, right? So you just start cutting tails and stuff like that, and getting smaller and smaller down, and then eventually when you get to near the very end of this process, you have a very small hyperparameter space that you're searching for, but you still have that kind of information about distributions. And that is the paper that proposes using Hyperband and Hyperopt together is like 3 weeks old, and actually no, I guess it's not even out yet because it's in open review right now, and you can see the comment of someone saying like, oh, it seems like you didn't do any work at all, and I was like, I don't know who this person is because that's a pretty smart idea. But yeah. Yep.
Did you submit your changes as PRs to the main?
I haven't yet, no.
Okay. Maybe they need a maintainer. Maybe you should be the official maintainer.
I thought about it actually. Yeah. I was gonna write him, the lead maintainer, an email about this before the talk, and then I just ended up looking at Gaussian mixtures for hours instead. So, yeah. Actually, just in terms of just where this field is going, this sub field, there is a consortium called AutoML that includes this plus a whole bunch of other people who do these kinds of algorithms. So like something called Teapot. Actually, I'll just get to this right now. I'll talk about that in a second. Let's just do, okay, what about neural networks? So there is like a templating engine for Keras, where essentially you just go like curly bracket. This should be a uniform curly bracket, but you just put that directly in your how you're defining your model. So that's called Hyperus. There's nothing in PyTorch that I've seen, but you could just use the regular Hyperopt library, which I've shown you how to use, and it's totally general purpose. You could do it for anything. Okay, other hyperparameter libraries. Hyperman, I talked about Teapot, which is kind of neat. It's a genetic algorithm, so essentially it just creates, say, like 100 algorithms, and then only takes like the top 10 or so, crosses them around, and then that becomes like the parents for the next generation. So this is a lot slower. The nice thing about this, though, is it can grow like really big pipelines. So you can get, as you were mentioning, so like maybe it's a normalizer, and then it's a PCA, and then you can actually get really weird stuff if you run it for very long, which I've tried before, where it's like make a random forest, but don't use a random forest. Just use that as more features for this other bigger random forest. And then, like, so you start getting these weird forking path pipelines that, in actuality, you're probably not going to want to use because they take a really long time to run. But it has a nice little feature where you can look at the Pareto optimum, which essentially just means like what is the best thing you can do for the complexity that you have that you're willing to accept. Scikit-learn. This is kind of cool because they've built up a database of a bunch of different data sets, and they're looking for different like kind of meta features about a data set. So number of categorical variables, how many levels that each categorical variable has, how big they are, etc. Blah blah blah. I found that it doesn't work great, but someone else should try it. Also, it learns whole ensembles of models instead of just one at a time, so you can get it to be like, what are like the 5 best things that work best together? Question.
So if you want to, tune your hyperparameters, which one of these libraries do you recommend?
The one that I helped write. So, I helped write. I changed a few things, but the one that I doodled on, I recommend. It's just so easy to use. Okay, that's it. Here's the bibliography. Any more questions? Yes.
In terms of the SP, to get the best combination of the hyperparameters, which one of them actually? Which is the best results in the shorter time?
Buy 100 instances and run random search on the 100 instances. Just do that, and then it'll be the fastest. It'll cost you a lot, but it'll be fast. Yeah.
Actually, that brings up like a question I forgot. Did it help you distribute it, or are we building?
Yeah, so instead of picking exactly what the quantile will be, you kind of pick like the asynchronous quantile. So it's not as accurate in terms of picking like a good and bad distribution, but you can actually make it distributed. Does that make sense?
So it will somehow collect together this
yeah, so it makes a MongoDB instance, and then you send out workers, blah blah blah, and it comes back. I know that. Yeah, I hear you laughing. Yeah.
Why is that funny? Is it because it's Mongo?
Because it's web scale. Yeah, it doesn't matter.
Mongo's web scale.
Yeah.
It's MongoDB.
Yeah. Okay. Anything else? All right. That's my talk.
I actually have one last announcement that I actually forgot to mention. So turns out, actually, I should mention about the other meetups as well, like Goose asked me on the chat to do that. So just be aware that we also have like 3 sister meetups. Like one of them is called the Data Science Paper Reading Group.
That's happening this Wednesday, by the way.
Yeah, so where we all nominate a paper and we just talk about it. And then there's one for Kaggle competitions.
Learn data science.
Where, yeah, it's part of like Learn Data Science where, I think someone talks about a Kaggle competition, and it's a very good way to just kind of like, if you're just getting into machine learning, that's a good way to start because it's a real problem, It's a problem, and you see people solve it. So.
What's the third one?
And the third one is a Data Science Lightning. That's
the new one.
So we have another new Data Science Lightning talk where I think we have like 4 or 5 presenters, each presenting for 5 minutes.
Right.
So this talk started out as a lightning talk. Imagine me trying to fit all of this in like 5 minutes.
The next lightning talk is on July 25th. If you are interested as a speaker, I think there might be one more slot open. I'm not sure. You should probably there's a channel called Data Science Lightning. We should probably look for that.
Also, we are going to the local after this.
Before that, the next one is about your VP coming in. Do you want to announce that? Okay, you want to announce the next one, and we're looking for speakers?
Yeah. One last announcement is our next meetup for Vancouver PyData is about testing machine learning models. So if you have machine learning models in production, how would you test them? This is actually by a very senior engineering person at Flipboard. Flipboard is a magazine app that recommends, they have a backend that has recommender systems and topic modeling. So they've put in an entire system for actually testing these models. So on August 8th, we'll be talking about that. The speaker's name is David Creamer. We'll put up the details soon, so keep a lookout for that.
And we're looking for speakers.
And we're also looking for speakers. So if you do Python, anything related to PyData in any part of the stack, just feel free to reach out and reach out to, there's Boris, there's Anish, there's us, which is Arnie, me, Osama, Yves, he's not around, but just reach out, holler. The hardest part about doing this is actually having you come and present it, right? The easy part is finding the space, sending a few emails and setting everything up.
But still, if you have a space that you're looking to sponsor with,
that would be cool.
If you're looking to sponsor pizza, we're totally fine with that. Whatever,
whatever works. Very easy. Next Sunday morning.
We are pretty much all in grad school, so we are pretty like desperate. Like anything, like you said, like
any food is fine.
Yes,
Thank you. So that we should head to the local.